Hey guys, so you are in the Venus or Lunar class. I'm going to be making videos of the packets that we passed out on Monday. I know a lot of you guys prefer when we read things to you or listen to audio recordings of the reading, so that's what I'm going to do for now. If you are in Venus or Lunar, you guys should have the packet that has a planet on it. And the essential question for it is, why is it important to consider an author's point of view or purpose? I'm not going to spend this whole video reading the whole packet. Probably just, I think, the first 5 pages until we get to the first set of questions. You guys are responsible for the questions on the side of the sheet. So if you guys flip to page 168, there is a little heading that says cite evidence. You guys will have to do those in your packets, and you'll be getting graded on that when you turn it in. Just an FYI. So here we go. Saving the ozone layer. The Earth's ozone layer protects all life from the sun's harmful radiation. However, human activities have damaged this shield. Less protection from ultraviolet light has led to higher skin cancer and cataract rates and crop damage. The United States and 190 other countries have been phasing out production of ozone-depleting substances in an effort to safeguard the ozone layer. The ozone layer. The Earth's atmosphere is divided into several layers. The lowest, the troposphere, extends from the Earth's surface up to about 10 kilometers or 6 miles. Virtually all human activities occur in the troposphere. Mount Everest, the tallest mountain on the planet, is only about 9 kilometers, 5.5 miles high. The next layer, the stratosphere, continues from 10 kilometers to about 50 kilometers, or 60 to 30 miles. Most commercial airline traffic occurs in the lower part of the stratosphere. Next is the mesosphere. It extends to about 85 kilometers, or 50 miles. Meteors and other space objects burn up in this layer. The stratosphere is above that. It continues to about 650 kilometers or 390 miles above Earth. The northern and southern lights appear at this level. The final layer is the exosphere. It has been detected up to 10,000 kilometers or 6,000 miles from Earth. Satellites travel in this layer. Above this layer, the atmosphere merges into outer space. Most atmospheric ozone is concentrated in a layer in the stratosphere about 15 to 30 kilometers or 10 to 18 miles above the Earth. Ozone is a molecule containing 3 oxygen atoms. It is blue and has a strong odor. Normal oxygen has 2 oxygen atoms and is colorless and odorless. Ozone is much less common than normal oxygen. Out of each 10 million air molecules, about 2 million are normal oxygen, but only 3 are ozone. However, even such a small amount of ozone plays a key role. The ozone layer absorbs a portion of radiation from the sun. This absorption prevents the radiation from reaching the planet's surface. Most importantly, the ozone layer absorbs the portion of ultraviolet light called UVB, which has been linked to many harmful effects, including various types of skin cancer. Ozone molecules are constantly formed and destroyed in the stratosphere. The total number, however, remains relatively stable. The concentration of the ozone layer can be thought of as a stream's depth. Although water in a stream is constantly flowing in and out, the depth remains constant. Ozone concentrations vary with sunspots, the seasons, and latitude. These processes are well understood and predictable. Scientists have several decades of records that detail normal ozone levels during these natural cycles. Each natural reduction in ozone levels has been followed by a recovery. However, convincing scientific evidence has shown that the ozone shield is depleting well beyond changes due to natural processes. Ozone depletion. For over 50 years, chlorofluorocarbons were thought of as miracle substances. They are stable, non-flammable, and inexpensive to produce. Over time, CFCs found uses as refrigerants, solvents, and in other applications. Other chlorine-containing compounds include methyl chloroform, a solvent, and carbon tetrachloride, an industrial chemical. halons, extremely effective fire extinguishing agents, and methyl bromide contain bromine. All of these compounds have large atmospheric lifetimes. The longevity allows them to be transported by winds into the stratosphere. Because they release chlorine or bromine, CB11 to 20E, when they break down, they damage the protective ozone layer. The discussion of the ozone depletion process below focuses on CFCs. However, the basic concepts apply to all of these substances. In the early 1970s, researchers began to look into the effects of various chemicals, particularly CFCs, on the ozone layer. They also examined the potential impacts of other chlorine sources. Chlorine from swimming pools, factories, sea salt, and volcanoes does not reach the stratosphere. Chlorine compounds from these sources readily combine with water. Repeated measures show that they rain out of the stratosphere very quickly. In contrast, CFCs are very stable and do not dissolve in rain. Thus, there are no natural processes that remove CFCs from the lower atmosphere. Over time, winds drive CFCs into the stratosphere. The CFCs are so stable that only exposure to strong UV radiation breaks them down. When that breakdown happens, the CFC molecule releases atomic chlorine. One chlorine atom can destroy over 100,000 ozone molecules. The net effect is to destroy ozone faster than it is naturally created. Returning to the analogy comparing ozone levels to a stream's depth, CFCs act as a siphon, removing water faster than normal and reducing the depth of the stream. Large fires and certain types of marine life produce one form of chlorine that does reach the stratosphere. However, numerous experiments have shown that CFCs and other chemicals produce roughly 84% of the chlorine in the stratosphere. Natural sources contribute only 16%. Natural events such as large volcanic eruptions can have an indirect effect on ozone levels. Mount Pinatubo's 1991 eruption did not increase stratospheric chlorine concentrations. Instead, it produced large amounts of tiny particles called aerosols. These are different from consumer products with the same name. These aerosols increase chlorine's effectiveness in destroying ozone. The aerosols increase the efficiency of the CFC siphon. They lower ozone levels more than would have otherwise occurred. However, this effect was short-lived. The aerosols from Mount Pinatubo have disappeared, but long-term ozone depletion by chemicals continues. One example of ozone depletion is the annual ozone hole over Antarctica. It has occurred during the Antarctic spring since the early 1980s. It is not a literal hole through the layer, rather it is a large area of the stratosphere with extremely low ozone amounts. Ozone levels fall by over 60% during the worst years. Research has shown that ozone depletion also occurs over the latitudes that include the other continents as well. Over the U.S., ozone levels have fallen 5 to 10%, depending on the season. Ozone depletion is a global issue and not just a problem at the South Pole. Effects on ozone depletion. Reductions in ozone levels lead to higher levels of UVB reaching the Earth. The sun's output of UVB does not change. Less ozone means less protection, hence more UVB reaches the Earth. In Antarctic studies, the amount of UVB measured at the surface may double during the annual ozone hole. Another study confirmed the relationship between reduced ozone and increased UVB levels in Canada. Laboratory and other studies demonstrate that UVB causes non-melanoma skin cancer. It also plays a major role in malignant melanoma. In addition, UVB has been linked to cataracts. All sunlight contains some UVB, even with normal ozone levels. It is always important to limit exposure to the sun. However, ozone depletion increases the amount of UVB. That, in turn, increases the risk of negative health effects. Furthermore, UVB harms some crops, plastics, and other materials and certain types of marine life. The world's reaction. Initial concern about the ozone layer in the 1970s led several countries to ban using CFCs as aerosol propellants. However, new uses for CFCs were found in the 1980s. Production of CFCs and other ozone-depleting substances, or ODS, grew rapidly. Nations became increasingly worried that these chemicals would further harm the ozone layer. In 1985, the Vienna Convention was adopted to formalize international cooperation. Additional efforts resulted in the signing of the Montreal Protocol in 1987. The original protocol would have cut production of CFCs in half by 1998. After the original protocol was signed, new measurements showed greater damage to the ozone layer than was originally expected. In 1992, the protocol countries decided to completely end halon products by 1994 and CFC production by 1996 in developed countries. In the United States, Environmental Protection Agency (EPA) regulations phased out production and import of ODS. The U.S. phase-out has reduced in stages the number of ODS that may be legally produced or imported in the United States. That is where I'm going to stop for today. There are 5 questions on page 173 that you guys can complete from what I just read. If you guys are already lost in your packet, I read from page 168 to 173. If you guys have any questions, feel free to email me.